Hello and welcome to Allegion's presentation on wiring choices. My name is Gordon Malczewski and I am a senior product trainer for Schlage under the Allegion umbrella. I'm a certified professional locksmith. I'm also a certified fire door and life safety inspector and a certified physical security professional. A locksmith for over 40 years, and I've been doing corporate training for over 30 years. Based in Roanoke, Virginia. So I want to welcome you to this presentation. I want to thank you for taking time to learn a little bit more about wiring choices. So we're going to jump right into our topics for today's presentation. So we're going to give you information to help you recommend the proper size and type of wire used for typical electronic access control installation. This will be based on the power requirements of the devices that are being connected. We're going to go through some basic terminology. I'm going to be talking about volts, which is electrical pressure. I'm going to be talking about amps, which is the flow of electricity or the flow of electrons in a wire. We're going to talk about the American wire gauge, which is the size of the wires. We're going to talk about how to recommend or select the proper size and type of wires for a typical EAC system. And this will be based on the current requirements of the equipment and also the environment where the equipment is being installed. So let's say, for example, you happen to have some wire on hand and you want to install an electric strike with a power supply and a simple push button. You want to know if you can use the wire for that purpose. So how do you know? Well, you may be thinking to yourself, sure, wire is a wire. You may be thinking, well, I'm going to try it, and if it works, it should be fine. You may be thinking, well, maybe I think it needs to be rated for something. Or you may think, well, it depends. I'm not really sure. So you fall into one of these four categories. So here are some things that you would commonly see on some products or some literature or box that the components come in. So right here, we see that we have something that 12 VDC, and that stands for 12 volts direct current, or 24 volts DC, 24 volts direct current. Over here we can see something that says 6 AMPS, and then we've got this chart at the bottom of this slide that gives you some information regarding the length of the wire run, that's the distance between the devices, the voltage that is being applied, how far apart the products are is a direct relationship to the size of the wire based on the current. So these charts are pre-made. It's not something that you have to calculate, but you may be working with those charts as well to determine what size and or type wire that you need for the installation. All right, so we're going to start out with volts, and volts is similar to pressure. It's electrical pressure as opposed to water pressure, but there are some similarities between water pressure and electrical pressure. It works for a good analogy in this presentation. All right, so we can have either less volts or more volts. And you can see here on the right-hand side of the screen, we've got this flower, and we have a choice for how we're going to water. We can use a watering can or a fire hose. Now, obviously, the fire hose would give you way too much water pressure. That would tend to blow the plant away. Now, we're not dealing with a plant, obviously. We're talking about electricity. But let's say we have an electric strike. So when we get the electricity, first of all, it has to be transmitted from the power generating station. It has to be generated long distances. And the most efficient way to do that is to transmit it using extremely high voltages. So outside on your street, on the telephone pole, you're going to see a transformer that's going to step down the voltage. Actually, there'll be a series of transformers that are going to step down the voltage from that high voltage transmission voltage to something that can be used for devices inside the home. So we're going to use a transformer. So you can see a small transformer at the top of the screen. So we need to step down the voltage. Even though the voltage that comes into our homes or businesses is going to be too high for that electric strike. So we're going to have to use transformer to step down the voltage. Now, amperage is similar to the flow. You can think of that as being like gallons per minute. So amperage is the flow. Now, you can see if this little girl tried to take a water out of a hose, there would simply be too much flow for her to get a simple drink of water. Now, the terms volts and amps, you'll sometimes see volts abbreviated with a single letter V, and amps could be abbreviated AMP or with a single letter A, capital letters on both. So where did those come from? Well, those names came from the early scientists that did experiments with electricity. So we had Alessandro Volta that did experiments regarding electrical pressure. And then for amperes, it was André Marie Ampère, who did experiments with current flow or electrons flowing through a conductor. Now, just as a hose can give your garden a certain amount of water, the right wire, the correct wire size of wire, will give you the right amount of power. You'll give you the right amount of electrons flowing through that conductor in a safe manner. So the question is, how big is the hose? Well, in the case of electricity, we wouldn't be talking about a hose. We would be talking about wire. So we start out with number 8 AWG, and that stands for the American Wire Gauge. And that is the system we use for labeling the size or diameter of the wire. So if we have an 8-gauge wire and we want to make that a little bit smaller, we would take that brass or copper material rather, and we're going to draw it through a series of dies. So it starts out a little bit larger, and we're going to start drawing that through a series of dies to try and get it to a smaller gauge. And you'll see the smaller gauge is 12. Even though it's a higher number, it represents a smaller diameter wire. So that's the first thing you need to remember when you're dealing with wire gauge. The larger the number, the smaller the diameter of the wire. It's the exact opposite of what you might think. So as we start drawing that wire or that copper conductor through a series of dies, it'll eventually get smaller and smaller in diameter until that 8-gauge wire gets into a much smaller diameter and turns into a 12-gauge wire. So that's how wires are produced, by drawing the raw material through a series of dies until we get the diameter that we're looking for. All right, so based on the information that I just gave you, here we have an example of somebody walking a tightrope between two cliffs, and they're using a wire instead of an actual tightrope. So think to yourself for a moment, if you had to use either 18 gauge or 24 gauge as your tightrope, which one would you choose? All right, so if you chose the 18 gauge, you would be correct if you were looking for the larger diameter tightrope. So remember, the larger the number, the smaller the diameter. So in this example, you'd probably want to use 18 gauge wire. Even though it's a smaller number than 24, it's actually larger in diameter. All right, so we're going to take a look now at this illustration. So on the left-hand side, we can see we're supplying 24 volts. Now, EAC systems typically use 12 or 24 volts. Those are the two most common voltages that are used for EAC systems. We have an electric strike here that draws 0.29 amps of current. The 24 gauge wire we see here, that is rated for drawing or conducting 0.25 amps. The larger diameter wire down below, the 18 gauge wire, that's designed to handle up to 0.75 amps, or 3/4 of an amp. So what this illustration is showing you, that in order to safely install or wire up an electric strike that draws 0.29 amps, we would have to use 18 gauge wire, because that will safely handle 0.75 amps. The 24 gauge wire is not quite large enough because it can only handle 0.25 amps, which is less than the electric strike is going to draw. So if you try using that, it may work eventually or initially, but it is going to start to generate heat due to the resistance of the wire. And if you get too much heat, it could result in a fire. So you always want to make sure you have extra current capacity in the wire to handle the current drawn by the devices. All right, so you may be thinking to yourself, well, but wait a minute. If I have 18 gauge wire, I wonder if it will supply too many amps, because I showed you the rating before. It has more current carrying capacity. So will it supply too many amps if I try and use it? So the answer is no, it's not going to cause a problem. It will not supply too many amps. Extra amperage capacity of a wire is okay from a safety standpoint. Now, when it comes to cost, that's a different matter. All right, so capacity and current draw. So you can think of the wire the current as being similar to sucking water through a straw. So the electric strike is rated to draw 0.29 amps. So it's only going to draw as much as it needs, 0.29 amps. So just like you would when you suck on a straw, you're only going to draw as much water as you need to satisfy your thirst. The device is what's going to draw the current. It's not the wire itself that determines how much wire is going to be drawn. So 18 gauge, once again, will handle 0.29 amps in this example anyway. And the electric strike draws 0.29 amps. So you should be okay. Now, it's usually a good idea to have a little bit of extra current carrying capacity for the wire, just to be on the safe side. Now here we see an example where the electric strike, this particular electric strike is drawing 0.59 amps. The 18 gauge wire can handle 0.59 amps, or it's going to attempt to pull, it's going to attempt to pull 0.59 amps through that wire. Here we have an electric strike that's going to draw 0.89 amps. And if we have the current carrying capacity of the wire only 0.75 amps, it's going to tend to draw too much amperage through the wire. So this wire was not rated for 0.89 amps, so it's going to draw too much current that will not be able to be handled by the conductor. It's going to start building up heat and could eventually result in a fire. So you always want to make sure that the conductors that you are using are rated for the amount of current that the devices are going to be drawing. All right, so now the technician's saying, well, why not use the larger gauge wire all the time? That way I only have to stock one diameter wire and I don't have to worry about calculations, and it simplifies my inventory. Well, the reason is the cost. So conductors are typically made out of copper. Copper is relatively expensive as a raw material. So typically you don't want to use a larger gauge than you need because it's going to be more expensive. Also, the larger gauge wire, the larger diameter wire, is going to be a little bit stiffer and a little bit more difficult to work with, either when you're pulling the wire or when you're making your terminations. All right, so let's take a look. We've got this particular chart here. So look at the top. It says we've got the voltage is 24 volts DC. On the left-hand side, we have a number of feet in the wire run, the distance between the devices. The tops of the columns indicate different currents, so quarter amp, half amp, 3/4, and 1 amp. So depending on the amperage and the distance, it will determine what gauge wire you're going to use. So let's say, for example, you had a device that's going to draw a half amp of current, and there's 100 feet between the devices. It means that you would have to use a wire gauge of 20 AWG in order to get that to work properly. So once again, this chart is pre-calculated for you. You do not have to calculate this yourself. You can reference this chart. There would be a different chart for 12 volts DC. All right, so now we're going to take a look at interference. So we've got this radio tower that's broadcasting some music. You're in your car driving, and as you get further and further away from that radio transmission tower, the signal is going to get weaker and weaker. There's going to be a loss of signal as you get further away from the tower. Now, something similar happens in wires. When you transmit voltages over longer distances or longer wire run, there's going to be something called a voltage drop. And you're going to need to take that into consideration when you are choosing your conductors. Generally, the longer the distance of the wire run, the larger diameter the wire needs to be to overcome that loss that is caused due to resistance. All right, so once again, we're going to see the chart and see the relationship between these items in the chart. So as I pointed out to you, as the distance or the length of the wire increases, so here, for example, we have 100 feet distance, we can use a 24 gauge wire if we have 1/4 of an amp being drawn through the circuit. If you go up to 500 feet distance, you've got to go up in diameter. You have to use a much larger diameter wire, 16 gauge. So two things we can note from this chart, that as the current increases, the wire size increases. As the distance between the devices increases, the wire gauge or size of the wire diameter would also increase. So that's the relationship we're trying to illustrate here. All right, so take a look at these two devices. The one on the left is an electric strike. It draws 0.29 amps. The electromagnetic lock on the right is going to draw 1.5 amps. So which of these two devices do you think would require a heavier gauge wire? The electric strike or the electromagnetic lock? Okay, if you picked the electromagnetic lock, you would be correct. That draws 1.5 amps, so that would need a larger diameter, larger gauge wire. All right, so we have a technician that's talking to his supplier, and he's saying, Bob, I've got this 18 gauge wire on hand. I need to install the electric strike, shown on the right-hand side here. Is it okay to use the wire? So we've got 18 gauge wire. We've got a device that draws a 0.5 amp of current. So the question is, can we use that wire? Now you can see that the supplier is thinking about that. And one of the missing pieces of this puzzle is, what is the distance between the devices, between the device and the power supply? We need to know that in order to be able to answer the question, can I use this 18 gauge wire? All right, so if it's a 0.5 amp and 18 gauge wire is on hand, you could use it if you have 200 feet or less in your wire run. So that's how we could answer that. We need a little bit more information before we could tell the technician that yes, you can use the 18 gauge wire. The technician could use it in certain situations and not in others. It all depends on the length of the wire run. All right, so another question the technician has for the supplier is, Bob, I want to know what is the least expensive wire for me to use to install a maglock. And the maglock is going to draw 0.76 amps of current. That's a little more than 3/4 of an amp. And it's 200 feet away from the power supply. All right, so we got to look for 0.76 amps. So we can't use the 3/4 amp column. We've got to go up to 1 amp. We know it's 24 volts, so that's according to this chart, and it is 200 feet away. All right, so let's see if we can bring up this. So we have to go to 1 amp. We find the 200 feet on the left-hand side of the chart, and that we cross over, bring our fingers together, we can see that we would need 14 gauge wire. So 14 gauge wire is the smallest or least expensive wire that could be used for this installation. Now you can see 14 gauges is very large, especially for an EAC installation. 14 gauge is the same gauge that's used for home lighting circuits. So it's a fairly large diameter, so that's going to be a fairly expensive wire to use. But that is the least expensive wire we can use for a little over 3/4 of an amp, or we're going to bump it up to 1 amp, 200 feet away. That would be the smallest wire that we can use. All right, next comment. Bob, I've got this wire. I know I need 22 gauge for the installation. How can I tell if the wire that I have on hand is actually 22 gauge? All right, so we're going to look at some of the wire labels. So you can see there's a lot of information printed on the wire jacket. So we kind of have to decipher and zoom in on what we're looking for. Now remember, I mentioned to you that we're looking at the standard AWG, which stands for the American Wire Gauge. So if we look closely, we zoom in here, we can see 24 AWG. So that's an indication it is 24 gauge wire. So the technician's saying, well, I need 22 gauge wire. Is this an example of something that I can use? All right, so if you look carefully, you can see that this is 24 gauge. It's a larger number than 22 gauge, so that means that it's smaller in diameter than 22. So it's not 22 gauge. In fact, it's even smaller than 22 gauge, so I cannot use this for my installation. Okay, so here's another example. The question is, do you think that this is an example of 22 gauge? Take a look, see what you think. Is this an example of 22 gauge? Okay, so if we zoom in here, sometimes the printing is not all that clear, but you can see that it does say 22 AWG. So the answer is yes, this is an example of 22 gauge wire. All right, so far we've talked about voltage, which is the electrical pressure. We talked about the amperage, which is the current flow through the wire. We talked about some of the labels that we're going to come across, which is the gauge of the wire, AWG. We've seen some examples of 22 gauge, 24 gauge. So now that we've done that, we've got to take a look at the environment where the devices are being installed. So a ceiling, above a suspended ceiling, would be an example of an environment. So the technician's saying, Bob, I'm going to install an electric strike today. I want to use some wire I already have. I know that it's the right gauge because I've already looked at the chart. I need to know if there's anything else I need to consider before I use the wire for my installation. So the supplier is saying, well, tell me where you'll be running the wire between the devices. So this is where we consider the environment where the wires are being run. So here's an example of a wiring run. You can see that we've got an electric strike that's going to be mounted on the door frame. The wire is going to be run up the frame and across the suspended ceiling to the power supply. So the environment where part of the wire is being run is above the suspended ceiling. That would be part of the environment where it's being installed. All right, so here we see a suspended ceiling, and we take a look at this suspended ceiling. There's a number of things of interest to us in that suspended ceiling. So first of all, we've got a supply vent. Let me see if that's on the next slide here. Yeah, we've got a supply vent, so that's going to be supplying heating and cooling air to the environment. We also have a return duct that's going to take the air back to the system to be recirculated. Now we also have some fluorescent lights. We also have some sprinkler heads. And it looks like we've got some conduit for some wiring that's running up to the workstations. Now our concern is what's going on above that suspended ceiling. All right, so if we lift up one of the ceiling panels and look inside, we can see that there is some ductwork attached to that return duct. All right, so that is going to take the return air, take it back to the HVAC system and recirculate it, but it's going to do so, that return air is going to go through an actual duct. Now, sometimes ducts are not used for the return air. Instead, the space between the suspended ceiling and the underside of the roof is used in effect as ductwork. So you've got air flowing through that space. That space is known as an air plenum. Now we have to watch what's installed in that air plenum, because if there is a fire, the smoke will be recirculated throughout the building. So there's very specific code requirements for the types of things that are installed in that air plenum space. And what we're concerned with when it comes to wire runs is using plenum rated cable. So plenum rated cable is going to be fire resistant. It's designed not to support flame. So if you pull the flame away from it, it will not continue to burn, and it will generally emit low levels of smoke. So that will reduce the risks associated with using wires in the air plenum space. So the wires, the jackets are typically made out of Teflon. Teflon coated cables will suffice for use in an air plenum. So how do you know if it's plenum rated cable? Well, you're simply going to look for the letter P as in Paul. That will tell you it's plenum rated. So here we have an example of something that would be found on a box potentially, and that is CMP. CMP. So CM simply indicates that it's communication cable, and then P would indicate that it's rated for use in a plenum space. So CMP, anytime we see the letter P in that series of letters, that would tell us it is in fact plenum rated. All right, so let's take a look at this particular cable. Look at the letters and the numbers, see if you can determine if this is plenum rated. So remember, we're looking for a letter P as in Paul somewhere in that lettering string. Okay, so if you said yes, that it was plenum rated cable, you would be correct. You can see here it's labeled CMP, that P is a little bit distorted, but it is in fact the letter P. So this would be an example of plenum rated cable. Okay, another test for you. Take a look at this cable. Do you think that this cable is plenum rated? Remember, we're looking for the letter P. Okay, so if you said no, if you thought that this was not plenum rated, you would be correct. You see it is labeled CMR, not P, but R. So R is an indication that it is riser cable. riser cable. So what is riser cable? Well, it's cabling that rises between the floors of a building. So for those types of wire runs, we do need to use riser cable. So there is a difference between riser cable and plenum rated cable. So anytime the wire is being run between the floors in the building, we don't want to have the flames traveling up the insulating jacket of the wire. So that's why we use riser cable. Now, plenum rated cable actually has a higher rating than riser cable. So plenum rated cable can be used in an air plenum space, and it can also be used as riser cable. But riser cable cannot be used in a plenum space. Okay, so the plenum rated cable has a higher rating. So another example of a plenum space would be if you have a raised floor in an IT department where they're running a lot of cables. That is also considered a plenum space. All right, so now we've got an example of a box, the label on a box that the wire comes in. So the question is, do you think that this would be an example of plenum rated cable? So take a look at the numbers and letters there. See if you can decipher whether or not you see that letter P anywhere. Okay, so if you said that this is plenum rated, you would be correct. Here we can see it, CMP, communication cable, plenum rated. All right, so we talked about the environment then. We talked about ceilings, area above suspended ceilings, oftentimes being a plenum rated space. You can tell if the return duct does not have actual duct work, then chances are that is in fact a plenum rated space and that it does need plenum rated cable. Or if the cable is going between the floors of a building, it must be a riser cable. Plenum rated cable has a P, riser cable has a letter R. Now the next factor we need to consider is interference. All right, so the technician's saying to Bob, well, I've got this product I'll be installing in a manufacturing facility. I have some wire, I know it's the proper gauge, but I want to make sure that I can use it. So the supplier's saying, manufacturing facility, there are some other considerations there. And that is electromagnetic interference. So you can see the description, or the definition. It's basically anything in an electrical circuit that can interrupt, obstruct, degrade, or limit the effective performance of a circuit. So it's anything that's going to interfere with the proper operation of the circuit. So here we have the example of that radio transmission tower, driving away from it. We've got the radio signal. Now, if we drop a tall building between us and the radio transmission tower, we'll get the clear signal. We'll be able to hear the music until we get between the building and the transmission tower. That signal is going to start to get garbled and it will degrade. So that building is in effect interference. So in an electrical circuit, there are things can cause similar types of interference. So here we can see we've got a power supply on the left-hand side, then an electric strike on the right-hand side, and we've got some machinery between those two devices. So as the signal travels up the conductor, as it gets near that manufacturing equipment, it's going to start to cause interference in the circuit and degrade the signal. So what causes electromagnetic interference? Well, any type of electric motors have the potential for causing electromagnetic interference. A large magnet, such as those used in diagnostic equipment in hospitals, would cause electromagnetic interference. Anything that has an extremely high voltage, like the power lines coming into a building, can certainly cause electromagnetic interference. Even things like sunspots. You've probably heard talks about sunspots affecting the electrical grid. Things like wireless phones or cell phones could cause interference. Anything that has a heating element, whether it be a toaster or an electrical heater, could cause electromagnetic interference. Now here in the suspended ceiling, there are some additional sources of electrical interference. Now these are fluorescent lights, and fluorescent lights are going to have a ballast, which is a type of transformer. Those transformers can also cause electrical interference. Now here we have an example of a real-life story that occurred with one of our devices. Here we have a hand key reader, a Schlage hand key reader installed on the wall inside an office, and the customer was saying that there was intermittent operation of the hand key reader. So we had a technician go out there, check the installation. Everything seemed to be fine. Couldn't find any defects in the device itself. until they walked around to the other side of this wall. And this was a factory, manufacturing facility. They saw a huge motor as part of the production equipment. So that huge motor was causing electrical interference, and that was causing the device to work intermittently. So that's why we definitely want to stay away from motors when we're working with access control devices. All right, now here's an example of some typical wire used for an EAC system. So you can see we've got this outer gray jacket. Now, if we peel away that outer gray jacket and look inside, we can see some silver coloring. It almost looks like tin foil. So there is a foil lining surrounding those inner conductors. If we peel away that foil, we can see the individual insulated conductors inside. So that foil jacket is designed to eliminate or reduce, at the very least, reduce outside interference, electromagnetic interference. So it acts as a shielding agent. So we can use foil. We can also use braiding to provide shielding. Now, normally when you have braiding, you're also going to have some foil shielding as well. So where we find braiding most often would be in closed circuit TVs, because the braiding makes the wire much more durable. So the braiding, in addition to the foil, will provide excellent protection against outside interference. You also find this in the TV. If you have cable TV coming into your home, it's going to be using braided cable. All right, so now the technician's saying, Bob, I've got this product I'll be installing in a manufacturing facility. I know I have the right gauge wire. Can I use it? All right, so the supplier's saying, well, okay, it means that you're going to be laying the wires near some electrical equipment, which could include things like fluorescent lights. Is that correct? Technician says, yes, it will be installed near fluorescent lights because I'm going above a suspended ceiling. All right, so as a result of that, we're going to fill in the blank here. So if that's the case, we've got fluorescent lights that could cause interference. What do we need to use? Well, we need to use blank cable. So what kind of cable do you think we would need for that installation to protect against the interference? All right, so if you said shielded cable, you would be correct. So we have to have shielded cable to protect against the transformers used in the fluorescent lights. So we look at this, we ask ourselves, is this cable shielded? The answer is yes, that cable was shielded. Now, there are some other ways to provide shielding. A conduit is another method for providing shielding or armored cable. Conduit is certainly going to be more expensive, at least, well, not only from a labor standpoint, but a material standpoint. It's much more difficult to work with. But conduit and armored cable will provide shielding. Now, the cable on the right-hand side, you can see that we've got a drain wire right here. That is in addition to the foil. So that drain wire will tend to funnel away or drain away any interference. Drain wires would be connected to ground, so it'll take that interference and take it away to ground. Drain wires should only be connected at one end to ground. If you connect both ends, it tends to serve as an antenna and could potentially make the interference worse. All right, so we covered all the power requirements. We talked about voltage, amperage, the labels you'll find on the wire, the gauge or size of the wire. We talked about the environment where the device is being installed. Above a suspended ceiling would be an example of an air plenum. And then we talked about devices, things that could cause interference, like transformers and fluorescent lights and motors found in manufacturing facilities. Talked about ways to mitigate interferences by using shielded cable, braided cable, conduit, and also incorporating a drain wire. All right, so now we're going to go into our final practice, see if we can review some of the information that we covered in this presentation. So we've got a building in mid-construction. We're going to do a walkthrough. All right, so we've got a technician doing an installation here, and we want to make sure the cable is plenum rated. The installer is saying, well, the electrician told me that I needed to use shielded cable, and I want to know if this is an example of shielded cable. So take a look at that cable. See if you think that if this is an example of shielded cable. What do you think? All right, if you said yes, it is, you would be correct because it does say CMP on it right here. So CMP, the P indicates that it is plenum rated. So that is an example of plenum rated cable. Okay, so here we have another installer. We've got this 24 volt electric strike, draws 1/2 amp of current, and I've got 24 gauge wire. I want to know if that's going to be acceptable. So we've got a device drawing 1/2 amp of current. I've got 24 gauge wire. Can I use it? Well, we have to ask ourselves, first of all, how far apart are the devices, or the device from the power supply? What is the length of the wire run? Okay, so the installer is saying it's about 80 feet. So once again, we've got 1/2 amp, 24 gauge wire, and 80 feet. So if we bring in this chart right here, so we know that it's 24 volts. We look at the column says 1/2 amp, and if we go to 24 gauge wire, and it's about 80 feet apart. So once again, 1/2 amp, 24 volts, 24 gauge wire. Okay, so 24 gauge wire will not handle that requirement. So we need 1/2 amp of current. Up to 100 feet requires 20 gauge wire. So 20 gauge wire is going to be larger than 24. So the answer is no. We cannot use 24 gauge wire for this particular installation. Okay, next scenario, we've got a ceiling. It's not an air plenum. All right, so the ceiling is not an air plenum. I still worry, though, whether or not I have the right type of cable. So let's take a look. Now, the dotted lines that just came up on the screen, that's an indication of where the technician plans on running the wires. So in some cases, we've got the cable laying right over the fluorescent lights. Here's an example of the cable. So once again, the question is this the right cable for use in this installation? It's not plenum rated. It's not an air plenum, but the question is, can I use this? So what do you think? Okay, if you said to yourself that yes, you can use it, you would be correct, because this does have the foil jacket on it. So that would mean it's going to mitigate the interference potentially caused by those fluorescent lights. Okay, so that's going to wrap up the presentation for this session. I do want to provide you with some information on some additional resources. So we've got the Allegion.com/US, and if you go under the training tab, you will find some additional training resources. If you go to the online courses, you will find some additional courses that you can take. We do have a blog called idighardware.com. This is written by our very own employee, Lori Green, who is considered an expert in life safety codes related to door hardware. A lot of good case studies, a lot of good question and answer. Great place to go if you have questions regarding life safety codes and door hardware. We also have a knowledge center. This is where there are frequently asked questions posted on all of our products, whether it's Schlage, LCN, Von Duprin, Steelcraft, or Falcon. Great place to go to get some additional information. If you want a catalog or technical manual, go to the Allegion.com website. And if you have any technical questions regarding any of our products, call customer care and they will put you in touch with our tech support departments. So we talked about a number of things in today's session. We talked about voltage being the electrical pressure. We know that voltage has to be stepped down in an EAC circuit. Typical voltages are 12 or 24 volts DC. DC is direct current, and direct current is not what comes out of the wall socket, that's AC. So we talked about that. We talked about current. Current is the amount of electricity that a device draws, and current will affect the size of the wire. The more current a device draws, the greater the diameter of the wire. We also talked about the size of the wire using American wire gauge, and one thing we learned is that the larger the number, the larger the gauge wire number, the smaller the diameter of the wire. So it's the exact opposite of what you might think. Then we talked about the differences between cables or the environment where the wires are being installed. We talked about air plenum, the fact that that may be a space between the underside of the ceiling or the roof line and the area above the suspended ceiling. If there's no ductwork on the return duct, that's an indication it's an air plenum. You have to use plenum rated cable. You can tell it's plenum rated because it has the letter P in it. If you're running wire between floors, then you need to use riser cable that has the letter R on the wiring jacket. And we talked a little bit about interference, the fact that things like fluorescent lights, electric motors, heaters can cause interference in the circuit that can degrade or affect the signal that the devices are receiving. To mitigate that, we're going to use foil line cable. The cable may also have a drain wire. We can also use braided cable or conduit or armored cable to mitigate outside interference. So we talked about all of those devices. So I hope you picked up some useful information during this presentation. That's going to conclude the presentation, and I hope you take advantage of some of our other resources. Thank you very much.